So let's talk about scientific method. Scientific method, scientific inquiry is all the same kind of idea. It's kind of the basis for how we think. It is, we see something and we are trying to explain what is going on. We don't know exactly what's going on. We don't have a person there telling us. So how do we go about figuring out what's going on? Well, scientific method allows us to establish a set of criteria at each step that allows us to come up with conclusions that are both valid and can also be considered unbiased. You know, typically people would see something and they say, oh, that's caused by that. Well, how do you know? So this allows us to really dive into why stuff happens, which is what science is. It is why is stuff going on around us. So let's talk a little bit more about the scientific method. Observations is the first step. We always start off with we see something, we have a question about something, what's going on? So science is about asking that question. It has to be something that's repeatable and occurring. If it's something that happens sporadically, it's going to be very hard to test something. It has to be something that we see all the time. You know, if every time we open the door, we see the same, we get shocked the same way, why is that happening? Why is every time I'm opening the door, I have an electric shock? So for example, why do chemistry students always fall asleep in class? I'm always going to get it this year, and that's why you're watching this video at home, so you don't fall asleep in my class. The next thing is we do our background research. So if I talked about that door, I always get shocked when I open up the door. So I want to look at other experiments. I want to ask other people, do you get shocked when you go into your door? You know, what causes an electric shock? And I look up all these different types of things. The key here is you want to know the difference between your fact and a theory. A fact is something that is concrete, is always going to happen. There's no chance that it will ever deviate. It is absolutely true. It is a fact that gravity works. Okay? It is here. But what is a theory is what we have a pretty good idea. We're pretty sure it's going to happen, but we're not 100% sure. A lot of stuff we're going to deal in chemistry this year is a theory because we cannot get to really an individual level and see and mess with and all of those electrons. We have to do other things to mess with them. We have a pretty good idea, but again, it's atomic theory. So, create a hypothesis. A hypothesis must be testable. So I go in, I know that I get shocked by the door, I read about static electricity in the carpet and wearing socks. So I'm going to create a hypothesis, something that I can actually test. It must attempt to explain or answer the original question or observation. So I want to know why I am getting shocked. So I have to come up with a hypothesis. Well, I notice that I get shocked in socks, but I don't get shocked in tennis shoes. So I'm going to make a hypothesis, is that every time I walk in socks on the carpet and touch the door handle, I'm going to get shocked. And only when I wear socks. Can I test that? Yes, I can test that statement. That statement is completely testable. The key word is you don't want to just say this is going to happen. You want to have something to say this is going to happen when. So be specific, be concise, and be consistent. So specific and concise. Keep it short and simple. Go. Next is the experimentation. So you're going to create a set of procedures. Make sure they test the hypothesis. This is really important right here. You don't want to have an experiment that doesn't do anything to support your hypothesis. You'd be surprised at how in college this is very, very common when you start to design your own experiments. You want to go back to that hypothesis and say, what is this doing to help my hypothesis? You want to set your independent and dependent variables. Remember, your independent variables are what you set. Okay? So if I know that I can wear the socks and I can wear tennis shoes, that's my independent variable. I'm changing that. Okay? Dependent variable is what is affected. Affected by the independent variables. Okay? So when you have a dependent variable, for example, if I'm getting shocked or if I'm not controlling that. All I'm controlling is whether I'm wearing socks or tennis shoes, and the shocking, that will definitely come from whether or not that independent variable is happening. Variables again. Independent, what you decide at the beginning. You want to set your independent variables to where they are the only thing that is changing. I don't want to be wearing socks or shoes and let's say I'm going to wear wet socks or wet shoes or whatever. I want to be sure that both of them are dry because I'm comparing them. I don't want to have any other factors that might affect my results. Your dependent variable depends on the independent variables, okay? So I don't want to mess with this, and I want to be sure this is allowed. I call it allowed to be, because if it's allowed to be and nothing else is affecting it but the independent variables, then we're good, okay? Does weightlifting make you run faster? So this is a question that a lot of people say, well, weightlifting would make you run slower. So if this is my hypothesis right here, this is my observation, my question. Obviously, it's not my hypothesis because it's not a statement. My independent variable is how much I would lift. So let's say I can adjust the lifting, how many times a week I lift, etc. I can control all of these factors. What I can't control is how fast I run. Okay? So if I want to gauge, again, I'm going back to testing this statement. I want to take a 40-meter dash time, a 10-yard acceleration, however I want to judge what fast is. I don't want to see how much ice cream they can eat. That's not going to answer this question. But, if I want to say just weightlifting, I need to make sure that my independent variable is here with the weightlifting and that I'm controlling that. My faster would be my dependent variable. So let's talk about the analysis. This is really where you get into your calculations and your proof. Whoa, goes crazy. This is really where you get into your calculations, your proof, and you want to be sure that anytime you're doing calculations, you are going back to this hypothesis. If you have observations, this is where you're going to go back to that hypothesis. Calculations are going to be quantitative evidence, like quantitative, okay, quantity. Qualitative is going to be about qualities, which is going to be your observations. Mainly in chemistry, we're going to deal a lot more with calculations. With calculations, you must show your work because guess what? Your work is your proof. If you don't have any work, people are going to believe these numbers came out of nowhere, and you want to say, no, this is how I did it, this is the way it goes. It also helps you if you have problems with your analysis and you can't quite get up to it. You want to see if your results are accurate. So once you figure out your answer, you want to say, does that make sense? So if it doesn't make sense, then you've got to go back, look at your calculations and all of those types of things. You also want to know what those results tell us. What are the numbers going after? What do they give us? What are the units? What do we notice? If the mass goes up, why is the mass going up when it should be the same? These numbers are important. You have to know what they're telling us. Specifically, again, going back, everything goes back to that hypothesis. Your conclusion. Here's where you reject or support that hypothesis. Again, you're going back to that hypothesis. That hypothesis is important. You want to go back to it. You want to say. You also want to support why you are rejecting it and why you are supporting it with evidence. So that's where you go back to your analysis and say, look, I got these numbers. These numbers indicate, because they're the same, and indicate there was no loss in mass, etc. So support with evidence, keyword. You also want to know what can be taken away from this experiment to be used in the next. This allows you to kind of apply what was discovered, what was seen in this experiment to something else. You might talk about the application of this experiment. For example, we went back to the mass. As far as conservation of mass, if the masses are the same, this can explain conservation of mass. This can be done with liquids or any other type of thing. You want to be able to apply what you've learned here to other stuff. Could this support a theory? Remember, a theory is repeated. Okay, it's a repeat of the same evidence. Okay, A theory is going to be, I get the same results every time. One thing I want to add here is error analysis. This is really where you go into why could error occur. And we'll talk about this in a later slide. But error analysis is important. Did you completely dry your sample? Did you calculate your numbers wrong? Did you measure wrong? Those are all things that could be a part of your error analysis. This is something a lot of people forget and a lot of people lose points for on major lab reports, is that error analysis. Also supporting with evidence. That's another thing that a lot of people get points deducted, because here's the deal. Don't tell me you told me so. I want to know why you're telling me so. Last thing I want to talk about is hypothesis, theories, and facts. Just a quick little overview. Hypothesis is a testable statement. Okay? It's not something concrete. I can test it. Keyword, specific and concise. A theory is a hypothesis that has been supported multiple times by experimentation, but is not completely sure. Okay? We see it over and over again in experiment. We have a pretty good idea, but like with the Big Bang, we weren't there. The theory of evolution, we weren't there. We don't have visual proof. Some people would argue that we have some pretty good stuff, but the fact is we were not there. Molecular theory. Again, we don't know exactly what's going on because we still don't have the technology to support that. Technology will change this. The last thing is a fact. It's concrete, always true. Newton's laws, gravity, those are always true. Something in motion will stay in motion until stopped. Energy cannot be created or destroyed. Those are facts. They are always true. Okay? And this concludes our presentation over scientific inquiry and gives you guys a few pointers about this. If you need to go back, watch this video again. Make sure in your notebook you've got some great Cornell notes, because we are going to use this in class, and you better believe that your first lab report, which is going to come up pretty soon, I'm not going to ask you guys to go through this process in as much detail as possible.